Next up is Dr. Jayson Bursill. He is a data scientist for Delta Controls. Is that International Building Technologies? Excellent. Where he leads all data science and related research activities. Jayson received his PhD in mechanical engineering from Carleton University for developing and implementing model-based predictive HVAC controls and evaluating the performance in a field test. He is also an adjunct research professor at Carleton University. Jayson is published on multiple building-related topics in several academic journals and conference proceedings. In addition to his experience and expertise, Jayson is also involved in several ASHRAE technical committees, TC 1.4, GPC 36, SPC 223P, and SPC 231P. Let's all welcome Jayson to the podium.
Perfect. Thanks so much for the intro there. So I guess, well, I talk a bit about what I do and kind of details of it. I was explaining this actually on my way in. I initially started really purely as a data scientist, which, has anyone here taken data science courses or interacted with data scientists much? A lot of it's clustering, pattern fitting, stuff like that. And don't get me wrong, I still do a lot of that, but I found kind of more foundational issues in how to actually scale a lot of artificial intelligence and even machine learning algorithms in our field, which is what kind of drew me to take a bit more of a research-focused path and to expand a little bit of what I was doing into things that I feel are kind of more on the fringe of artificial intelligence, but really enable a lot of things. And it's a pleasure to go after Jean-Simon because he gave a great background on artificial intelligence, generative AI, and kind of the broad capabilities, but I want to kind of zoom in a little bit after I give a little bit of a history lesson of AI on how do we do this everywhere, right? How do you not have to talk to me about this anymore? So learning objectives, you guys are going to kind of see this later. Things like define artificial intelligence, I think that's important. Distinguishing between different applications. And figuring out field requirements for advanced algorithm configuration in a timely manner. So I always start with defining artificial intelligence. Booms and busts. The world is a cyclical place. This is why we have sign functions to describe things. And it's not much different with artificial intelligence. This isn't the first time people have been hyped out artificial intelligence. Who was around in the early 90s, right? It was crazy for artificial intelligence. And even before that. Scalability is a big thing. I'm going to get a bit in the weeds there. I hope people learn some new stuff to look at after today, which I think is the important part. And some applications that start with individual devices where the I/O inputs and outputs for people that aren't crazy controlled junky people, they're statically positioned. So you know where it is, you know where the data is coming from. It's not fully programmable. And that's kind of the easier application where you can put this stuff in now because it ships as a packaged unit, right? Then starting to go up to higher level stuff that you can do with systems once you start to have enough metadata to leverage. I very briefly talk about AI-assisted coding, which actually, how many people here know how to program Python? All right. How many people that don't know how to program Python think that they could mess around with ChatGPT or something like that and figure out how to do it a little bit? All right, good. And I like that because I think that's very real right now. And then, of course, predictive control, which I wrote a thesis on it, and it gets me up in the morning. So what is artificial intelligence? I like these kind of three concentric circles. Artificial intelligence, I think, is a bit more conceptual. I think back to, we had big data phases before artificial intelligence, which in a way, the big data, as we saw with the zettabytes, started to drive what we're doing with artificial intelligence today, right? But what is big data? And that's hard to define as well. Artificial intelligence is a bit loose, and I'll kind of talk about the Turing test on the next slide. But ultimately, you're imitating human behavior, right? It's a mirror of the things it's exposed to, so you can infer things from patterns, much like the cycles of humanity, right? Machine learning is a little bit more specific than that, where it references data and systems. Things like linear regression start to enter that territory where technically it's machine learning. You probably don't think it's machine learning, but you're taking data that is hopefully from the real world or something that you want to model with a machine, and you're making a mirror of the real world by fitting a line, which all of these are really just a ton of weird lines. And then deep learning specifically digs into it more, where you actually have to have an artificial neural net model. For those not familiar, the artificial neural net model is intended to model the firing of a neuron in the brain. So you kind of have an output, and it can be binary or analog, which makes it even more confusing. So it could be a 0 or a 1, or a scale, probably from 0 to 1. And then that's kind of at the basis of all these transformers that we've been talking about, with a new mechanism on top that I'll talk about a little bit of where it came from. So, brief history of artificial intelligence, kind of going all the way back. Alan Turing, Enigma code, crazy guy, lots of analog computers at the time, which was crazy. Bugs were bugs, right? Literally. So, this is the guy that first developed the Turing test, right? And the Turing test is actually a qualitative test to determine artificial intelligence, where you have to convince the human that it is a human and not a robot at least 30% of the time, right? But each human's threshold for being convinced that it's actually a human and not a robot is variable. And for the ASHRAE 55 comfort people, it's kind of the same idea, right? It's all over the place, and even that gets a bit qualitative, but we like to throw a number on it, right? And kind of still on this Turing test thing, think about today, right? How many people are convinced things in the web, on social media, or things are real people, but they're not, right? So that's kind of the world we live in, and we've kind of reached, what even is the Turing test anymore? Artificial intelligence gets defined in 1955. You have kind of the first wave of, well, I guess the second wave of AI after that. The first wave is kind of, you have computers and punch cards, and you can start to do linear regression on a punch card. And I'll show a graph of that. Then you start to work through to things that were building up at a bit of a valley up to what we have today, right? And lots of crazy stuff happened in the 2010s. I started to stop care about updating this graph about 2022 because GPT-3 came out, and new models come out basically every week or so. Who remembers DeepSeek and how crazy that was and how nobody's talking about it now, right? Yeah. So there's no point in updating this graph anymore because we hit GPT-3, and now nobody wants to make a simulator online because the whole internet is a simulator now. So artificial intelligence hype cycle. Talking about cycles, everything goes up, everything goes down. I try to update this every year. I probably need to update it for 2025. I'll get around to that soon. Things are going to move. But you see generative AI, where it's kind of is here, and there's stages to this. Who's heard of the concept of hype cycle before? Okay, perfect. So some people have. But basically, you have excitement through innovation trigger. People start to expect a lot of things at a certain point. And I think that's where we are with generative AI, which is what people are talking about primarily, and why I like to talk a little bit about machine learning in my presentation as well. And then other things that start to enable this technology, which is where if you see knowledge graph there, this is particularly interesting because I think the knowledge graph is a really overlooked part of what has to feed these artificial intelligence generative AI systems. And I'm going to drill into that a bit today. But everything moves. When I first started talking about this stuff, the generative AI dot was like right at the top of the peak of inflated expectations. But you think in terms of value to people and value to our industry, really when you're climbing up that slope of enlightenment is when you start to really see applications solidify at scale. Example being computer vision. Occupant counting has become very effective with cameras. It's accurate. It's starting to get more and more scalable every day. So that's kind of an exciting thing that's in, the plateau of productivity where you can start to trust it a bit more. Autonomous vehicles, not so much yet, but it's climbing. It's got a bit of a horizon to it though. So booms and busts. Typically with artificial intelligence, I have found it's been driven by the hardware, right? Boom one, you have computers and a bunch of money as, you're at the end of World War II. People are still really excited about trying to win the war. And there's still money flowing, right? Money, hardware, innovation, there's a theme. Boom 2, you start to have personal computers, maybe even a lug around if you have the money for that, right? And then you have different countries putting money into different computing innovation projects. This is where you start to see expert systems, heuristics, maybe even getting to the point of meta heuristics, but you're still kind of limited. You're not on a punch card anymore. Bugs aren't usually literal bugs, but it could be still, maybe still today if it gets in the fan. Um, yeah, don't knock it till it happens. All right. But that was really based on kind of rule-based stuff. And a lot of the technology that happened in Boom 2 is still very applicable today and derives a lot of value in our industry today. Now I think we're living in the heart of Boom 3, video card, massive parallelization. You can see how the stock markets reacted to this. So there's a ton of projected growth, but I have a feeling history is going to eventually repeat itself. So we need to. Exactly. The cycle's going again, right? So I think part of this is being able to find the things that will derive value and get us through the next bust until the next boom. And who knows what that's going to be. People tell me maybe quantum. I can't predict the future. If somebody has a crystal ball, please tell me. So modern applications, I'll do this really quick because we've hit a lot of these, but I want to kind of visually show the type of things I'm thinking about when I think of this. Translation changed a lot in 2017, and this was referenced in John Simone's presentation. Google put out a real landmark paper from their AI research team around that time, and that was roughly when I believe the transformer was essentially invented, built on top of deep learning. They added something called an attention head mechanism, which allows you to navigate all the deep learning. And the visualization was fantastic because that's what's happening in the bottom of that, right? And now you can put a bunch of stuff on top of it, which is what you see on the right. You can get it to write text because it's a large language model. And it's also getting pretty good at writing code. I'm going to talk a little bit more about that later and how I think you can use that directly to leverage data modeling technology and potentially integrate directly into control these days. Then, of course, you have self-driving or even kind of lane assist features within vehicles. So that's more stuff where you have computer vision systems and you have a bunch of neural nets. That's more of a machine learning thing. And it's focusing more on kind of sensor signals and a model that's specially fit for that rather than integrating with a language model off the shelf. So how can we scale this in buildings? Well, I think the first thing is the PhD needs to be out of the loop, right? There aren't enough PhDs with knowledge of how to do things with AI systems in this industry to actually fix every building in this industry. So I hope someday that I have less of a job. Maybe not no job, but less of a job, right? And this is kind of the important part. So how do you get the systems ready for the machines? And how do you get the machines ready for the systems? I start to think of the movie Armageddon, right? Like you have to kind of take some people and move them a little bit more. I don't know whether you want to put like drillers into space, but there has to be a little bit more of a crossover, and this is where the data world starts to come in. So I think machines need to be able to identify systems. That's really important. Machines need to be able to tune system models. And I specifically made these distinct because I don't think that machines should tune systems totally. There's a lot of work that goes into kind of base level control where you're dealing with, who here is familiar with PID, proportional integral derivative controls? So it's like this magic machine where you put in a few parameters and you can kind of tune how fast you get the thing to go where you want it to go and how effective it is at that. That in and of itself is a subsystem that can cause a lot of problems if you mess with a really fast acting system. So that's why I think a lot of what we do should kind of focus supervisory level or it's something where the system doesn't change too much, right? Optimization constraints, you have to be really careful with those. And I'll show a bit of an example of that later with respect to predictive control. And all of it needs to be operator intuitive because ultimately the operator is the one that truly controls the building and they do, are they unpredictable things? Maybe. And they're intuitive to their own situation, but it's hard for us to build a model of the operator to understand what the operator is going to do, right? So kind of thinking from their perspective is very important. Simple bottom-up problems. This is a bit of a different perspective. I'm thinking like, you start with like sensors, things you put on a breadboard, and then kind of work up from there. That's kind of my angle of where I come to this automation problem or artificial intelligence problem. Then, of course, being compatible with kind of contemporary supervisory control. ASHRAE has a guideline called ASHRAE Guideline 36. It's called High Performance Sequence of Operations. Whether or not you fully agree with all the algorithms in there, it does give you some specification over what sort of inputs and outputs are in the system and how a system could operate. So this gives you a baseline, and a lot of research that does go into controls. Typically, we'll use ASHRAE Guideline 36 as a baseline when they're comparing whatever they're doing in artificial intelligence to it. So I want to kind of highlight a lot of emerging standards for controls and metadata. This is where I think it gets important because the metadata is the important part I want everybody to remember after this. There's also stuff outside of ASHRAE that kind of feeds into things within ASHRAE. So kind of skipping Guideline 36 a bit because I talked about that already. Standard 223P was kind of built on the foundations of BRIC and Project Haystack with respect to metadata. I'm not going to go too deep into all of that yet, but I'll define some core pieces. But ultimately, the goal of this, once they remove the P, which P on that means it's proposed and hasn't been fully published yet, is you will have normalized data classes for everything in a building automation system. And then you can start to understand that, the machine can understand that, and these natural language models can now go in and they have a full definition of the thing they're looking at, right? And it's normalized. It's an exciting time, and I think it's getting close, right? I'm not going to put a timeline on it, but people are getting excited. And BACNet's moved a little and actually recognizes the data format that's in 223 now, which actually BACnet is the cognizant committee for 223, which is weird because usually it's a technical committee in ASHRAE for technical junkies out there. Then there's ASHRAE standard 223P, which is controlled description language. So the idea behind this is you could use the class definitions in metadata with a real world system that's got full programmability, stuff can move, but it doesn't matter because you've classified it. You can package algorithms from Guideline 36 in a functional block, and you can start to automate the engineering of the automation system, right? So this is what gets me really excited because now you can kind of start with this hardware. You can connect things to hardware. You're reading digital signals. You've mapped the digital signals, and you can start to really build stuff out rapidly. So I kind of have 4 S's of semantic interoperability that I like to refer to. It's been talked about already, but kind of system/transport level, things like BACnet, other protocols, there's a ton of them out there. It all has to go to one place to actually use all the data. You can't control a system that you can't get feedback on. Well, you can, but I wouldn't recommend open loop control. It's very inefficient. Life safety is where you might use open loop control, but even then, right? Then you start to get to syntactics, which are these dictionaries I'm talking about, BRIC, Haystack, 223. How do you actually label these things, right? How do you take the letters out of a dictionary? It's not telling you how to build a sentence, right? That's the next thing where you get to structural specification. But it is giving you set language and set definitions for the verbiage in that language. Then you get to structural specifications, and this is a bit of the Wild West right now, and I'm trying to wrangle in it a little bit. But how do you specifically store the metadata, and how do you operate within the constraints that are given by the syntactics, right? And there's work to be done in that area. Then kind of final frontier that I don't think we'll ever get past is context, right? And I show an example of that on screen, and this is kind of, I like this because you can talk about a plant, but it could be a green wall, or it could be a large array of boilers and chillers. It could be both. But hopefully, once you've done the other 3 things, you can now figure it out from the rest of the context, but maybe not. There's inefficiencies in human language. So metadata sources. This is an interesting topic, and I played around with something called optical character recognition, which is where you start to scrape the text in something like the table on the right there. And unfortunately, it doesn't work very well, but the text on the image to the left of that. So you could start to put it into a machine readable format. studies I've done on this, it's good at like PDF pictures of paragraphs of text. I think people have been doing a lot of that for a while. Fun fact with optical character recognition, you can use some sort of AI-assisted code generation system, and it's pretty good at building you about 25 lines of code that you can feed it a PNG file in something like Python, which is very exciting. It took me very little time to test this. Tables aren't bad because you have white space around things. Being able to delimit it with commas and things like that becomes a bit complicated. Anything with overlapping lines, like the actual mechanical drawing there, not great. So I would highly recommend when you start to put data into these types of systems, if you're thinking from like a mechanical, electrical, plumbing perspective, if you do have a table of everything that you can get easily out of the drawing package and give it to people to do stuff with that data, please do, right? Because the image path, there's a lot of overlap. Information can be lost in translation. And I know this data exists in the BIM world. I've been told about it. I've seen it. You know, you have industry foundation class and all sorts of weird XML formats that exist in that space. And I think we're close. It's just being able to get this into a way that easily transports to something that's ingestible by, you know, basic programming languages, right? And once you start to try to represent this stuff, all of the building metadata standards, and I believe even Haystack now through Haystack 5 is starting to move towards this concept called the triple. Triple, I'll contrast it to a tuple. So a tuple is very common in programming. You have a key and a value pair. There's two things, tuple. Then you have triple, which is three things. So you have a subject, which is the origin. You have an object, which is the destination. Then you have a predicate that relates the two. Where this is very important and why you would go with the triple instead of a tuple is now you can build out a full hierarchy all the way up and down the system. And you can start to see how everything relates. And you can start to get to an endpoint, and you might have like device 100, analog value 1, present value. And you can map that all the way up to even maybe what PDF drawing package it came out of, right? For reference, or what air handling unit it's part of. And this is where, when you start to look towards connecting large language models or even advanced algorithms that have specified input classes to these systems, this is very important because you can start to map the system. So the standards are emerging, and this is kind of an exciting time where how it's applied is really going to be interesting. And before I start to get into examples, I wanted to really quickly go over the concept of an AI system validation process. Where typically you want to be fairly comfortable with things before you put them out in the world. This can apply for research, this could apply for products, this could apply for anything. So you would start with a proof of concept. You develop models in parallel with data collection because you can't collect data from the past before you've started collecting data. And then you put all this together where you start to develop models, you start to develop an inference pipeline, the framework around it. You integrate it. You have to have some kind of quality assurance process no matter what you're doing, whether you log into a computer daily and you're like, oh yeah, this looks like it works, right? And I've done that before. It's frightening. It's better to put actual things in there that notify you. And then the process is iterative as you kind of continue to improve things. And I think this is kind of a good example of, at a very high level and from a very simplistic perspective, the type of things that someone's going to want to think about as they're putting together anything that uses data to model the world. So starting with some applications here, this one's debatably artificial intelligence because it depends whether or not you consider a Kalman filter artificial intelligence. It's more of a sensor fusion thing. I get excited about it, and there is a model within it that then updates, and it's recursive, which means it's taking the most recent data to update it. So it's not totally machine learning, but it does take data points that feed in with a time series perspective to it. So something that was interesting here was putting a sensor cluster on the ceiling where you have, well, the focus here was being able to read temperature. So operating rooms are kind of a weird case because you have to condition them very carefully, and you have the air curtain that goes over the wall, which is typically where you put the temperature sensor, the thermostat. And then, of course, once you have the cool air that's going into the operating room moving over the thermostat, that really throws off the temperature reading, right? And you're not really reading ultimately what your goal is, which is to condition the temperature of the warm stuff in the center of the room, right? That's really what you're trying to do. So in this case, using infrared temperature, which is kind of an interesting problem because when you're doing infrared temperature, you now have temperature to the power of 4. So whatever you do goes wrong at the power of 4 now. And then compensating that with an onboard temperature sensor. So this got kind of exciting, comparing the composite temperature value, which is what I described, with wall sensors and return duct sensors. I don't like to show the graph because it takes too long to explain. But ultimately, in this case, when you're starting to measure the temperature remotely, there's less hunting. So for those not familiar with hunting, you can kind of more smoothly modulate the actuators of the system. So the damper's not moving up and down a lot. You're not gushing air into the room and then choking it and then gushing it and then choking it. Response was better. The temperatures presumably were more accurate using the Kalman filter approach. And room cleaning is a big aspect as well. Stuff splatters everywhere in an operating room. You don't want to clean that. Well, you have to, but you don't want it to go into your thermostat. So kind of taking the same idea of a sensor cluster and putting more stuff in there on top of the composite temperature sensor, an application that I thought was kind of interesting, constrained to a device again. So the data model things I talked about, we're not there yet. I'll have more examples for that later. But you're starting to pull in things like relative humidity, luminosity, microphone data, closed circuit, and most importantly, PIR sensor data. And this is where it gets interesting and where this particular application really needs to be on an edge device, because when you are starting to process the passive infrared signal, which I'll show on the next slide, you're doing it at much more rapid intervals than you would in a typical logging environment on a building automation system. You're doing it several times per second. Now, to compare this to kind of more accurate systems, larger scale systems, we use the metric persons within 2, PW2, which is exactly what it sounds like. It's figuring out what amount of the time the estimate of occupants in the room is within 2 occupants. Typically, our goal, going back to the AI model validation process, was to keep that above 90%, which was, we kind of found qualitatively was an acceptable amount of error for most people trying to operate a system and modulate ventilation and kind of figure out space usage. Oh, let's see if this video works. It does not. So I was going to show an image of the analog to digital count, kind of what the bits are coming in at from the sensor itself and how it moves over time. And then the number of people that it was estimating and how it would compare to a ground truth, which is, in this case, we used a camera, but kind of, working all the way down. I've also evaluated different camera systems and then literally had a guy with a clicker be like, yeah, that's 2, that's 1, right? Which that's like the worst job ever, but it's necessary and ground truth data is important. But ultimately from this, the idea is that you can take raw sensor data at the edge, moving at a higher frequency than you would most traditional backnet data collection through like a trend log or whatever you're collecting data in that's like a trend log. And then access this directly in backnet through some different downsampling processes to take the noise out, right? And this whole concept of downsampling, which is where you apply a model more rapidly than when you report the model, allows you to take a lot of noise out of the result of a machine learning model. I've written a paper on this before where you kind of you look at hourly level data, and then if you aggregate it up to about a month, it's actually pretty close, right? Which is, it's weird. It's one of the mysteries of data, right? But this was kind of exciting, and kind of keeping the camera thing out and then being able to work with sensors you would put in a room anyway, I think is quite exciting, because I feel like to get more machine learning into buildings, you really have to work with what's there. And you have to kind of build around use cases where you can improve everything and keep it reasonably cost effective. So ultimately, the good part about this is within the constraints of building this type of a model, you have assumptions, right? Like a floor to ceiling height of 10 feet. The room's hopefully a rectangle and not like an L or a U, because the passive infrared sensor actually has to see the thing that's emitting infrared energy, right? So that's kind of a limitation of it. But most meetings that we actually looked at in this study were 6 occupants or less, right? 86%. And then when you get to the bigger ones, like it's a lot of people in a small room, turn it up, right? So now I'm going to get into generative AI and like a little chat bot that I put together that surprised me briefly. But I like to do the generative AI disclaimer that I generated with generative AI. Generally, I agree with what it says. Um, all of it, again, going back to how artificial intelligence is just a mirror of things it's looking at. Accuracy, data sensitivity, bias, that's all related to that, right? The model is only as good as the data that it is trained on. Then, of course, once the user uses it, there's interpretation and responsibility. And ultimately, I feel the usage of generative AI, large language model tools specifically, what comes out of that is the responsibility of the user to kind of act on that appropriately and constrain it appropriately, right? And when I was wandering around ASHRAE, someone said this, and I felt it was really fitting for these types of systems. It's almost like talking to real people. A lot of the time you'll get good answers. Sometimes you'll get absolutely crazy answers. And who's heard of hallucination before with AI? Yeah, everybody has. Yeah, so that happens. I mean, people hallucinate too, right? But, oh, this didn't show up very well. So my apologies for that, but I showed kind of complicated modeling stuff, and I'm going to show a more complicated model that's really just a VAV box later. But how do we take data that usually would have existed in namings of points, kind of tags you would put on things that are cooked up by kind of how you would delimit or how you would constrain something to like 4 characters, right? And I think you can actually leverage large language models to start to work with this through, as was discussed before, these RAG systems, retrieval augmented generation. So once you start to have data in tables and things that could be used to map stuff like a CSV table where you have like IAT is indoor air temperature, right? And then you do that for a bunch of different things. You can start to feed that in as what's called a knowledge base into these large language model retrieval augmented generation systems. And you can start to do some exciting stuff. You could even put in templates of systems. You could put in templates of models, and then you can map what's in the model to things that you can put into the actual physical system when you program it. And this is where it gets really exciting. And it got kind of cut off there. But you could see you can generate your own names for points based off of kind of some sort of tag mapping that it could figure out itself. It could do something based on what's in the model, which sometimes they'll do weird stuff. So you might want to actually constrain that. But then you can also use it to generate point addresses and property references to the point where you could start to connect a large language model with other sources of data that are domain specific with a model out of the box and like a GUI wrapped around it because people don't like to do command line. And then start to build something that can then be used to directly generate things that would be in a backnet or something like that building automation system. So now you have semantic data models, or could, and then you get to the point where you can start to leverage the data a bit. And this is a really simple example. There's people that do crazier stuff than this. This is something I did as kind of a proof of concept to test the semantic data model and the data mapping. But this was done with the bot framework. The time GPT-4 Turbo was super exciting because you could actually spit a PDF out of it. That was really new. Now it does all sorts of weird data I/O. And then billing data was exchanged back and forth with a BACnet API. Actually, on this point, who here has heard of BAC0 or BACO? Nice. That's an interesting Python package. And if you're not dealing with kind of weird stuff in BACnet like Secure Connect, it's a great way of starting to engage with a BACnet system with Python code. There's, of course, different vendor-specific packages for doing this, but I like people to learn more about BACnet. So Python's a great place to start, and that's all built on something called backpipes, and the national labs always use that type of stuff, right? So the prerequisite for being able to do this is you need to have some sort of a data model underneath, right? And the data model has to have things that are in natural language that can then be understood by the large language model to retrieve data from the system. That's kind of the nuts and bolts of all of these fundamentally, right? So this was just like a really basic thing that my co-op student did, where he asked the temperature of a room. Once we identified the room, it gave the current temperature. And a piece of side context that's actually really important here is this was not a real temperature sensor. This was a virtualized container that we kind of hosted on a computer. And because of that, the value didn't change. The value was at the last real value that the point read, so it wouldn't move, which it figures that out. So we start to then leverage the data model because you can then go through the relationships of things and then figure out what's the time series history for this specific point. That's what the machine does in the back when you ask, what is the value 1 hour ago? So it starts to retrieve the value from that array. Then, of course, it finds that the value is the same value as before. Now you start to ask the value over the last 7 days because you're thinking, this is weird, assuming it's a real building. And the system itself actually figured out something fishy was going on. And then it kind of writes you a paragraph, but you don't want to copy paste that because why would you? You have PDF output. So you could actually ask at this point in time, GPT-4 Turbo, the vanilla version, to write you a report where it kind of put that together. It's an exportable PDF. People still love to do things by PDF. So you got to kind of live in the world we live in. And it does a bit of analysis of the trend, and it gives you kind of basic off-the-shelf administration advice where, you know, given the flag status, go look at the room, right? Is something wrong there? If you're asking 3 questions about this point, maybe you need a more rigorous monitoring and maintenance schedule. And then if it's really important to you, maybe you need to have some temperature sensor redundancy there. So how do we get semantic data models today, right? So the triple stuff that I showed you guys, really it just has a bunch of tabular data that can go into it to generate something like the thing on the bottom here, which this is just a VAV, a variable air volume terminal system in brick, right? It gets a little bit more complicated when you actually get to ASHRAE 223 because you get down to specifically having to say what the units are of the property, what media is going through it. Is it air? Is it water? But that gets kind of exciting. Why I don't want people to be afraid of this is you could take stuff that would come out of a typical automation system, BACnet, whatever. All that could be exported as a table because you can read the properties because all that is just a table. And then you can actually use large language models today to help you build that code there. I was panicking at one point because I had to build a semantic data model of a building in about 6 hours. So I tried to kind of use AI-assisted coding for this, and this was able to instantiate a Python library called rdflib to build a bunch of functions that could take that table and build that model, which then now can be leveraged by AI tools. So kind of pulling back on this a bit to something that I'm a little bit more, well, I wrote a thesis on this, so I get excited about it. Yeah, that's how I would describe it. But predictive control, this is kind of the thing everyone's trying to work towards. The vast majority of systems today are reactive. Even ASHRAE Guideline 36 is reactive. Stuff built around ASHRAE Guideline 36 is reactive. Predictive control has a large amount of data requirements, right? So how do you take this large amount of data requirement that needs to be mapped into a system and actually integrate this effectively and rapidly? And this is where I want to leverage all the stuff I talked about already, because now you have a data model. Now you can write functions that take that data model and can figure out what the actual direct mapping is in natural language, and it gets kind of crazy very quickly. But this starts to leverage a lot of stuff where we're going back to kind of weather models as well, right? So ultimately, the building is going to kind of be at the mercy of the ambient conditions. Well, whoops. And kind of depending on the type of building, the amount of glass, the climate, this has already been talked about, but you're going to have kind of different things that are more important to the thermal response of the space with which you're trying to control. And this is where you have to put all these things into more of a classical predictive control algorithm. But what I'd focused on in this study, which is very data hungry. I'm not ready to do anything with this yet, but this is where it would go if I had that data. You could start to figure out what input points are really important, right? And the concept here in the machine learning world is called drop-off, where your multiplier or parameter or whatever it is that goes in front of the thing goes to 0, and then the input drops off. And that's no longer important. You don't have to map it. You don't have to maintain the ingestion to that point. Which this had like 100 different inputs, but ultimately it cooked down to The indoor air temperature, the set point, a 2-hour ahead outdoor air temperature dry bulb forecast, and an occupant prediction in the next hour. Will people be in the space in an hour? And is that meat going to heat the room? Right? With the ultimate output of this being, do you run the existing system and the existing algorithm business as usual? One, that's great. You can just put it in front of a line of code, right? Or do you override to another mode? Do you shut the system off and let it just free float? Zero, right? And I like to go with enumerations on this or integers or something that has like set modes, because you're not starting to try to rewrite sequence of operations completely. It's something that could kind of ride alongside in terms of predictive control, and you kind of don't make it too risky, right? And the existing constraints are still valid to the system primarily, and I'll get into the caveat to that later. But this was the setup that I did this on. There was a ton of sensors. This was an institutional building at a university. It was actually kind of a lab building. They were testing some animals there, but that wasn't my part. No. They specifically told me, don't go anywhere near the animals. And yeah, please, all right? But these were kind of office spaces attached to that, and there was 27 offices. Some of them are multiple rooms per zone, which that's a bit of a weird thing to manage, because different rooms are going to have different demands, and different rooms are going to throw a 0, different rooms are going to throw a 1. What's your threshold to do something? And I leave that up to the integrator to figure that out for the use case based on the criticality of what you're operating, right? But ultimately, going back to kind of that how do you test an AI or machine learning algorithm? It's very much an iterative process. In this case, there was 2 floors, and they were pretty much identical. So the thermal properties of the space were pretty close, but the occupants were different, and the occupant always has an impact on the space because they ultimately have some control usually, maybe not, but usually. So this is where it gets kind of interesting, is being able to compare this and being able to look at a full-scale algorithm to a light algorithm, a lot like that tree that I showed that can be just a few lines of code that can go in anything that's line code or not, to then figure out how do you want to operate this space? Are you going to do something crazy or not? So ultimately, when you start to abstract this, and I'm not going to go into the math on this because it gets crazy. I wrote a couple of papers on this, and we'll write more. But the really important parts here is relative constraints, right? When do you stop doing the algorithm, and what are the limits of the algorithm's ability to act on the system, right? And here I used minimum and maximum zone temperatures that you would kind of allow, because this was a multi-objective optimization that looked at indoor air temperature difference from set point, as well as the forecasted energy use of the room. No utilities yet, but working on that. But ultimately, the seasonality was also important, because the model would change a lot. So you have to have either different models for different conditions or a model that self-adapts, right? And each of those has pros and cons. And ultimately, like, I think the constraints and the adjustments need to be in something that's easily visible and ingestible and workable for an operator, right? Which is why I've put this thing together where that comfort versus energy slider is actually manipulating a 6x6 matrix, right? But the operator doesn't want to see that. So kind of closing out, scale AI carefully. I know that's obvious, but I need to say it, because all phases of design and integration, you really need to think about this. Is AI the right tool for this, or can we scale down to machine learning? Can we do kind of basic heuristics? Do we want a large language model? Do we even need AI? Can a human do this? If a human can't do this, the AI can't do this, because the AI is trained on what the human would do, right? Semantic interoperability is very important. If you can't identify what the thing is in some sort of a natural language, which it can vary now because the large language models are very good at translation between human natural languages, but it has to have something to reference in some natural language, right? Applications constrained to individual devices can have a lot of success very rapidly because the I/O is static. And then I think once you start to get up to more complex system level stuff, everyone that's doing this has some sort of a data model in there that they're leveraging, right? But data models take a lot of work, and I feel like that is an opportunity to improve efficiency. Then, of course, ground truth data. You have to have actual human data from something that you're trying to model to build the AI application. Here's the learning questions. I guess they're on the web somewhere. Yeah, sure. So, do data-driven models have to be black box? True or false? Do I wait for an answer or do I just go? Yeah, okay, perfect. Who thinks they all have to be black box? Good. They don't. The biggest barrier to wide-scale adoption of predictive control in buildings is the model forecast accuracy. Who agrees with that statement? Okay, mixed opinions. I disagree with that. I think the biggest barrier is being able to rapidly integrate it consistently. Otherwise, the operator will override it. That's just my thought. You can disagree with me. Video card technology has driven the third boom of artificial intelligence. Who agrees? It totally has. Heavy parallelization. They're running a ton of video cards in all these crazy data centers. AI tools could generate code to manage semantic metadata. Who agrees? Okay. Either people are asleep or mixed opinions, but that's fine. I think so. And predictive control typically has over 30 inputs for even a simple VAV terminal unit. Who agrees? Yeah, it definitely does. It's a mess. Awesome. Well, thanks so much, guys. I'm happy to answer any weird questions you might
Thank you
have.
very much. Do we have any questions from the audience? Up there.
Thank you, Jayson. That was a great presentation. I just wanted to ask, when it comes to the model that you provided, you said the sensors at some point in time can kind of drop off and the AI system just generate what the temperature could be or the humidity could be. So eventually, I guess what I'm trying to clarify is initially you need these sensors, and as time progresses, you could remove them and the system operate all on its own.
Yes, and I wouldn't say specifically a temperature sensor, but when I said that, I meant kind of like forecasts of it, right? So you might need the 2-hour ahead forecast for a sensor, but you wouldn't need the 3-hour ahead forecast for the sensor, right? Things like that. So kind of each discrete forecast in time is its own input to these algorithms, right? It's an array ultimately that then has to be continuously updated, which I treat like an input in this concept. But you don't need all the data, and then you can kind of limit which part of that array that you use, and you can kind of manage how the data moves inside the data exchange system. So kind of what you said, but with clarification.
And one more, sorry. When it comes to designing these systems, why can't we start with a base model of what a typical, let's say, operating room should be like, and then use these sensors as feedback just to optimize the operation rather than start from scratch?
Yeah, and you absolutely can. I didn't talk about that. But yeah, and this gets to the concept of kind of archetypal gray box models. You can make it any variety. I prefer gray box because it takes me too long to build a white box model, and I don't totally trust a black box model, right? But ultimately, I do think that you should start with kind of set parameter values, and all this stuff kind of assumes certain constraints on those parameters, right? Like when you're looking at kind of your matrix transformation for the current temperature, and then going one time step ahead, that can't be more than 1 to keep the system stable, stuff like that. So that's still going to be in there, and you have kind of assumptions of where that would start in the constraints in your actual modeling process, right? But you can also start with a model that would be kind of close, and I wrote a paper on that I talked about in Building Simulation Rome in 2019, where you kind of qualitatively look at gray box parameters on a room for a bunch of rooms, and kind of there's an average value you would start with where the swing isn't that much, so it doesn't really matter, right? But it does, but it's not as bad.
Up top, we have a question over here. Great presentation, by the way. That was really interesting.
Thanks.
Have you looked into any kind of, I'm going to throw out a term I don't expect most people to know, but like a priori algorithm for finding unique commonalities between data that otherwise would maybe not appear to people. Obviously, when we all think of controlling temperature in a space, we intuitively think, well, let's look at the temperature. That's usually the best indicator, right? But maybe over time, as we start to monitor and have data from different types of inputs, we figure out there's this really crazy but very obvious pair once you start to look at the data set using computers that shows that this is actually maybe a better predictor for the room temperature needs. Have you gotten into any of that and started to explore some of those other types of like computer-based algorithms that are really starting to find their way into other sectors?
So in my past life as an energy manager, I did more of that. Currently, I've really been focusing on control-oriented models, which ultimately the constraint of that is when you are controlling a set point for a temperature, you have to kind of build around that, right, as the actual thing you're controlling. As far as inputs, I think there's a lot of opportunity there because the input ultimately is just an array of data that you've mapped through whatever your data map is. Have I explored much of this currently? Not recently. One thing that is kind of interesting when you think of things like ice rinks, right? Ultimately, your energy use, for example, is going to be so heavily based on the actual ice usage days and things like that, and it probably doesn't have much to do with the temperature at all, really. So not currently at a control time scale, but I have a kind of other time scales. And I think it would be interesting to do more of that, but I think ultimately with control-oriented models, that has to remain in the space of the input to the model rather than the control variable of the model, for people that get really into like state space control and PID loops. But I like that.
Hi, a question about scalability. You mentioned that for maybe like a single room, you can have self-adapting models or have maybe a set of 5 or 6 models, depending on the condition, but that's for a single room. If you're expanding to 1,000, 2,000 rooms, is there a way to have one model that will fit on all of those rooms? Or then do you have to scale to have 2,000 models, one for each room?
Yeah, so there's a lot to unpack there. For kind of an energy focused model, absolutely, I think kind of like a higher level model would be the way to go. When you're in the control space, I do think there is the horsepower on modern devices to be able to do this. You're seeing things that have like multiple gigabytes of RAM that are controlling a VAV box. This exists. And that's why I've been focusing on kind of putting models there. I'm going to reference towards ASHRAE Guideline 36 here with the concept of trim and respond control, which is why I like to look at the zone, because ultimately the air handling units in these buildings respond to the loads at the zone, right? Which is why I've been focusing there, because if the zone has a demand, that's going to feed a signal up, and some amount of signal is going to turn on the air handling unit, which drives your energy use, right? And all of it kind of trickles up in a way. So for actual control, you can do it and it has some effect, but it doesn't necessarily solve all of the issues down at the zone or kind of have an accurate input on the direct load, right? It's kind of an aggregated load that moves up. From an energy perspective, absolutely, right? But energy is going to be kind of more of a reactive rather than a predictive thing, right?
So is the conclusion that you can have one model across multiple buildings?
Ooh. So I think what you're trying, or what you're describing here is transfer learning. It's a concept where you have one model for one thing and then you can use that same model for something later. Somewhat. And that's where it gets into the data hungry meta heuristic thing that I showed, where I'm like, this would be great, but I need a lot of data to kind of confirm that this actually works somewhere else. I managed to do it for 27 rooms on a similar building, but taking that to another building, I think there's an amount of modeling that does have to exist with kind of similar things.
I guess what I'm asking more is like endpoints and hosting the actual model that's being used to create the predictive output. Can you host one model across these buildings, or does each installation need to have its model hosted somewhere? You know what I mean?
Yeah, well, I mean, you could centrally or distributedly host the model, right? So you can have one model per building, or you could have one model for multiple buildings if that model is valid for those buildings.
Yeah.
Does that answer?
That makes sense. My question was just more about like the scalability of having one model per building. Is that sustainable?
Oh yeah, totally. I think you should be having one model per zone.
Oh, okay.
Yeah, but it's a simple model. It's not a full model. It's like a
Right.
line of code that's just, it's almost algebraic, but technically it's not.
Okay.
That's kind of what I'm inferring.
Okay,
Yeah.
thank
But
you.
yeah, thank you.
Thank you, Brian. Thank you, Jay. You've been mentioning from time to time in your presentation about a thesis you wrote, you have a PhD in mechanical engineering. You and others starting in academia have helped to pull us all to here. This is very practical applications. You don't have a crystal ball, but could you take a guess as a natural intelligence when we might all be seeing these tools becoming business as usual instead of the exception?
Yeah. So this is tricky because the tools, I think, really rely on the ability to scale the tools. So I think once we do that, it will move very quickly. I think the thing that's going to be really a big flashpoint in this industry is once ASHRAE 223P becomes ASHRAE 223, right? And then after that, I think it's probably going to take 5 to 10 years to see a lot of that done effectively. So crystal ball, I think, is going to be 223 release, which could be 1 to mystery number of years. It might even happen next year. I don't know, right? Plus 5 to 10. But don't hold me to that.
Great. Thank you very much, Jason.
Yeah, thank you.